Okay, beautiful. So what I want to do for the second bit here is so first I'm going to take this will probably take maybe about 10 minutes. Talking about Russell's paradox and how it was a huge problem for what's called the naive conception of sets. Um, Russell's paradox, again, he basically came up with it right around the turn of the 20th century. And at the time, there was a kind of grand hope that we could give an absolutely firm foundation for all of mathematics and logic in terms of just basically this theory of sethood that I just sketched for you. There was one more axiom. And as it's going to happen, that one more axiom is the problem. Because note, what we haven't said yet is how many sets there are. We talked a little bit about it, but we haven't actually said that yet. I've just told you that there's this relation of membership. We talked about the nature of sets, how sets can stand in relations to each other, how once we have them, we can perform operations. But we haven't said anything about how many sets there are. And the problem, and Russell's paradox, attacks a very straightforward and intuitive answer. So, the intuitive answer was called the axiom of comprehension. The axiom of comprehension says, for any condition C, there exists a set such that for all x, x is a member of that set, if and only if Cx. In other words, right, for every predicate, there's a set corresponding to the members, corresponding to the things that satisfy that predicate. So think of any predicate you can come up with. There's going to be a set of all and only the things that satisfy that predicate. Dogs, people in the room. Dogs or people in the room. Buses that no one has ridden today. Stars no one has ever mentioned before. Again, come up with any predicate you want. There's going to be a set of the things that satisfy that predicate. So the axiom of comprehension, together with the axiom of extensionality, the one that we saw before, those gave us what we'll call naive set theory. And there was a hope at one point, because this is a beautifully simple system. Just these two, the basic notion of membership and the basic notion of subsethood, and we can get effectively almost all of that. The hope was this story would give us everything. Russell blew it up. And Russell blew it up because he pointed out that actually this doesn't work. So to get a grip on how we'll show why it doesn't work, let's talk about barbers. So consider a small town that has only one barber. And this barber is very neurotic. And they behave according to one strict rule. This barber, this is an old-timey barber, so shaves people. He shaves all and only those people who don't shave themselves. So if you don't shave yourself, then the barber will shave you. If you shave yourself, then the barber will shave you. Okay? So that's the barber's one rule. So here's the question. Who shaves the barber? Well, if he doesn't shave himself, then he must, because that's his rule, right? But if he does shave himself, then he can't, because that would violate his one rule. And of course, right, if he does shave himself, then he must not, which means he must, which means he must not, which means he must. Oh God, we're in a fucking loop. Right.
He shapes people who don't shape themselves. It isn't meant like people are quick thinkers and shape themselves. They're just shape themselves when necessary. So we don't mean that he's able to shape himself once.
But no, if he shaves himself once, right, then he doesn't shave only those people who don't shave themselves, because he shaved himself. He never breaks his rule, right? And even if he did it once. And in fact, if he got someone else to do it, then he would have to do it too, because that's what his rule says. So even he couldn't be hirsute, like he can't even have a beard, because if he has a beard, then he's got to shave himself. Oh fuck, right? We're in the loop, we're in the loop, we're in the loop. So again, it's a kind of joke situation, but it very nicely demonstrates the paradox. So here's the paradox actually set out. Given that sets can themselves be members of sets, there's nothing to stop some set from being a member of itself. Right? So let's have M be the set of all sets with more than one member. Right? Well, then obviously M is going to be a member of itself. Let's have N be the set of all things that are non-buses. Everything that isn't a bus is a member of N. Well, since N is a set, not a bus, it should be a member of N. So self-memberhood isn't really a problem. But let's have R be the set of all things that are not members of themselves. And given the axiom of comprehension, there should be a set for R. Because remember, to go back 2 slides, the axiom of comprehension says for any condition, for any predicate you can think of, there's a set of all of its members. So here's our condition. Being a set of all things that are not members of themselves. Okay, cool. So obviously, what's going to be inside this set? Well, obviously all the individuals are going to be in there, and a hell of a lot of sets. But what about this set itself? Is R going to be a member of itself? The problem is it must both be and cannot be. Because if R is a member of itself, then it must not be in there. Because remember, R is the collection of all things that are not self-membered. So if it's a member of itself, then it must not be a member. On the flip side, if it's not a member of itself, then it has to be in there too. Because remember, it's a collection of all the things that satisfy this condition. So it would have to be in there. But of course, if it's in there, then it can't be in there. And then if it can't be in there, then it must be in there. We're in the same loop that we had before. So, what's Russell's paradox? Russell's paradox is, given the axiom of extensionality, the axiom of comprehension can easily and very quickly get a contradiction. So naive set theory cannot do the work that we hope it would do, because at its core, it's contradiction. Before we go on, do we see the paradox? It is beautiful and simplicity and also joy. So what's the upshot? Russell's paradox indicates there's something rotten in the heart of naive set. And there's a couple things we might do to fix it. Set theorists have done a bunch of things. One option is to distinguish between what we call classes and sets. So what we have is the axiom of comprehension tells us something about classes. Classes can be funny and lead to contradictions, but sets, they're all behaved. The problem here is that you still get a contradiction with naive class theory. You have to do some more work. You can restrict membership such that sets can't be members of themselves, but this seems a little bit ad hoc. Again, think about for example, set of all things that are buses. That looks like it should be self-membered. You might attempt a kind of iterative hierarchy approach. So this is the idea that what we never do is get all the sets at once. We're just constantly building upwards. So a set couldn't be a member of itself in this way because it's not on the same plane as the things that are its members. Another option is to adopt the non-classical logic. This is something we're going to talk a little bit about the very end. So you might just say, yeah, some contradictions are true. So what? This is a nuclear option, but it's there. Put really bluntly, though, none of these are really terribly appealing. The best option is basically dumb comprehension. That naive comprehension axiom leads to problems, so we find a new way. And a lot of contemporary set theories coming up with various ways to tell us what sets are without getting us right back into the naive notion of comprehension and Russell's paradox. So that's really it probably for set theory. Again, to stress, the reason why I want to talk to you guys about this stuff is because I think this is really useful machinery to have in your back pocket. You'll come across some things in other discussions, in other bits of philosophy, and we were talking about this a little bit in the break. Right? Even just knowing or having a little bit of grip on what some of these symbols mean when you come across them. That's really the big thing for you today. I want you to at least be like, oh, I know, that's membership, right? Okay, oh, I know what it means with the squiggly brackets now. That's the kind of thing I really want you to drive for. Okay, before we get to relations, pause, ask any questions about the set theoretic stuff. Yeah.
Yeah, I know, no need for a legal question. My knowledge. So I put a paper having the yeah. So this will solve paradox. I understand what you say, but I don't necessarily see what you do.
So it's not a problem with extensionality. It's a problem with comprehension. Is non-self-member.
Yeah, so the can would be simply within that is itself.
Yeah. So the predicate is non-self-member. And there will be lots of things that satisfy that predicate. We all do. Because we're not members of ourselves. Membership is only a relation of individual standing to sets. Sure. Lots of things satisfy that predicate, no problem. The problem is, let's think about the set of things that satisfy that predicate. Let's call it Dave. Does Dave satisfy the predicate? If he does, then he doesn't. And if he doesn't, then he does.
So the problem really
Problem is coming back to this axiom of comprehension. We can formulate predicates that will quickly lead to paradox, and comprehension tells us there must be such a thing, so it is committed to this paradox. This is why some of the fixes will be basically replacing this axiom of comprehension. Find ways to restrict it so we don't end up committing to anything like this. As long as we can do that, we avoid this paradox. We might have new ones. We get out of this. Yeah, exactly. Okay. Other questions on the set theoretic machine? We'll talk a little bit more about it next week with possible worlds. And we'll talk maybe a little bit more about some of these other things going forward. But again, this is really just me trying to teach you a little bit about some stuff that will be useful later. Okay? Okay. So what I'm going to do, the last little bit here, we'll go through some stuff about relations. Now, here again, we talked about relations in bits and bobs, but what we haven't really done is talk much about their properties. So, relations, as you remember, right, we treated these in first order logic as multi-place predicates. So we had things like trusts, or loves, or is taller than. Now, what's noticeable about these relations is they will often have various properties. For example, is taller than. Nothing is taller than itself. So we might want to talk about the kinds of relations that are all like that. Or here's another cheap one. Is the same height as. Everything is the same height as itself. Even if you're no height at all, you're still the same height as yourself. So we might want to talk about all relations like that. So what we're going to do this last little bit here is I'm going to introduce you to some terminology. And this terminology will come back next week. And again, sorry, because it's going to be an absolute fucking assault of information. I'm going to try and go slow, and we'll talk more about it on Friday. So the first thing to talk about when we have a relation is it will have an arity. In fact, we talked about this when we first introduced them in FOL. The arity is effectively the number of gaps. A binary relation has 2 gaps. A ternary relation has 3. A quaternary relation has 4. You see how this goes. At this point, my Latin runs out. Quinternary relationship would be 5. I don't remember. 6 and 7. Whenever you have a relation, you will also have what we'll call the converse of the relation. This is basically just the relation read backwards. For example, whenever you have the is taller than relation, you also have the is shorter than. So if A is taller than B, B must also be shorter than A. Another one is you might think of loves and is loved by. If we read those as 2 different relations, what you have to do is change the order of individuals. A loves B, B is loved by A. Now, we can talk about whether the converse of the relation is something different or is the same relation just read backwards. There's an interesting metaphysical debate to be had there. What's important, though, is whenever you have a relation, you get a converse. So, that's our first thing. Now let's talk about properties of relations. Here's our first property of a relation. A relation can be reflexive. Relation R is reflexive if and only if everything stands in the relation to itself. So is the same height as is a reflexive relation in the sense that everything is the same height as itself. In contrast to being reflexive, you can fail in 2 different ways. You can be irreflexive, such that everything doesn't stand in relation to itself, is older than. Nothing is older than itself. Or you might be areflexive or non-reflexive. And this is when both reflexivity and irreflexivity fails. Loves is a good example. Some people love themselves, some people don't. That's why psychologists make a lot of money. Again, you see the thought. It's not that it's irreflexive, and it's not that it's reflexive, it just fails in other counts. What do you mean by more? It could be the other way too, right? Anything, right? These are just some examples, just to kind of give you the shape. What's important again is irreflexively, nothing can stand in relation to itself. Older than, younger than, more beautiful than, less beautiful than, right? Any of these kinds of things. Is a proper subset of. That kind of stuff. Again, these are just ways to think about it. So reflexivity means it always comes back. Irreflexivity means it never comes back. And areflexive means, well, maybe some of them do it itself and some of them don't. We talked about this stuff. We did this. Remember with the diagrams. Exactly, right? We did this, thinking about interpretations. This is just giving us some terminology to talk about things. Again, this is really why we're belonging to this. You will see these kinds of things in papers as you read. I want you to know what these terms mean. So reflexive is about whether it loops or not. Here's our next property. Next property, symmetry. Relation R is symmetric if and only if. Whenever A R is B, B R is A. That is, if it goes from 1 to 2, it goes from 2 back to 1. He's a sibling of. He's symmetric. If A is a sibling of B, then B, by God, better be a sibling of A. Again, we formalize them here as well. You can write the formalization down, you can just have it intuitively. Again, symmetric means it goes back and forth, right? So a relation is symmetric if whenever it holds, it always reciprocates. Now, much like reflexivity, symmetry can fail in two different ways. You can have an asymmetric relation, and this is just simply where symmetry fails, right? It's not the case that for every x and every y, if par x, y, then par way x. Loves infamously is one like this. A might love B and doesn't B with B, so I go back. Again, hates conveniently is also like that. A might hate B and B might not hate A back. Another interesting one is you might have a relation that's anti-symmetric. Now, an anti-symmetric relation is weird. It says for any x and any y, if x and y are each other, and if x r is y and y r is x, they must be the very same. So this is a way to characterize a kind of relation. It doesn't have to be reflexive. What it says, whenever you have symmetry, you have identity. So you don't actually even just have symmetry, you just have a loop. But note, anti-symmetry, to go back a slide, doesn't entail reflexivity. It could still be reflexive. Because all it just tells us is whenever the arrow goes between the two, oh, it must be the same thing all the time. An interesting relation here is part of. So in the notion of mereology, part is much like a subset. Everything is a part of itself. And in fact, if two things are parts of each other, then they must be the same thing. Another relation that we plug in here is subset. A is a subset of B, and B is a subset of A, and they must be the very same set. Note that some relations are neither symmetric nor anti-symmetric, at least as old as is a good example. So we may call this asymmetric. Different people use different terminology here. One last big property. We have reflexivity, which is about the loops. We have symmetry, which is about the kind of arrows going both directions. Our last one is one we talked about once before, but we never gave it a term. And this is transitivity. So a relation is transitive if and only if A R is B and B R is C, then there must be an arrow from A to C. So if A goes to B and B goes to C, then there must be an arrow from A to C. Complete the triangle. Taller than is a good example. Amanda is taller than Bert. Bert is taller than Carlos. Amanda must be taller than Carlos. Yeah, I'm using some things. Go the other way, right? Is poorer than. Amanda's taller than Bill. Bill is poorer than Carlos. Amanda's poorer than Carlos. See that? Yeah. Yeah. Yeah, these are just, again, you can fill in examples. What's important, again, is the property here. Transitivity holds whenever you can go, if you go from this to that, and that to that, you must have been able to also start from your first one and go to your third one. So reflexivity gives you loops, symmetry gives you back and forth. Transitivity says, hey, if I've got two legs, I can draw a triangle third leg. Much like the other two, transitivity can fail. You can have an intransitive relation. This is just simply when it fails. My favorite example of this is heats. If A meets B and B meets C, then A becomes C. A, B. Yeah, it's the circle of life. Yeah. Another good one is intransitivity. This is one where if A are B and B are C, then it's not the case that A are C. My favorite example of this is defeats in rock, paper, scissors. Everyone knows the game, right? Yeah. So notably, right, if A beats B, right, if rock beats scissors and scissors beats paper, then it is not the case that rock beats paper. It goes the other way around. Because you want to make sure that everybody beats somebody. So antitransitivity is effectively one where if you got the first two, you must not have the third leg. And intransitivity just means this doesn't universally hold. So again, I'm throwing in a lot of terms here. The ones that are really important. And understand reflexivity. It means you always have loops. Understand symmetry. It means you always get the back and forth, the bouncing. And transitivity. If you have the two, you must be able to draw the third. These are the important properties. Yes? These are just properties relations can have. Relations can have all or some of them. In fact, an equivalence relation is reflexive, symmetric, and transitive. So, you might fail to have something. So you might be reflexive and symmetric, but not transitive. You might be transitive and reflexive and not symmetric. Again, there's going to be combinations. We'll talk a little bit more on Friday about how these combinations match up. We might also define a Euclidean relation. So a Euclidean relation basically says if you start at one point and you can draw two lines out, there must be a way to draw an arrow between those two. For a long time, people thought a Euclidean relation was the same as an equivalence relation. It's not. It's interesting. But again, these are the kinds of things where what I really want to do is to stress for you the properties here. Again, no reflexivity, no symmetry, no transitivity. We have a grip on what these notions are, and we know that. Both of the exam, I think, we're probably going forward. Okay. Let me see. There's a bunch more. Yeah. So I'm going to quickly talk about a few more things, and it will not take long. This is just stuff to kind of say some more about how we might think about relations. Do not feel like you have to write the rest of this down. This is just going to be for funsies. Okay? So when we have non-reflexive or symmetric or transitive relations, we can force them to be. And we can force them to be or pretend that they are by talking about their relevant closures. So if I transform a non-reflexive relation into a reflexive one, I can talk about its reflexive closure. And we can do this basically by building up sets of ordered pairs. So if I started out with some relation, such as is taller than, Al's taller than Bart, Bart's taller than Charlie, Al's taller than Charlie, cool. Note, if that's the property, if that's the relation, what kind of properties does my relation have? A is taller than B, and B is taller than C, therefore A is taller than C. What kind of properties does this relation have? So we might take it, and to get the closure, we just add all the loops. And we could do this with symmetry, we could do this with transitivity. You take your basic extension, the collection of things that are actually doing the arrows, and you just add in the stuff that's missing to force it to be reflexive or symmetric or transitive. You'll see this sometimes in various papers. Again, just to let you know what it means to have this sort of closure. I'm not going to ask you anything like this, but I just want you to be familiar. We can also talk about partial ordering. We'll say a relation is a partial ordering if and only if it's reflexive, antisymmetric, and transitive. What this gives you is there's a foundation, some stuff at the bottom, and then it builds up. So you'll have stuff that's all at the bottom, that's reflexive stuff, and then as you keep going up, you get bigger and bigger and bigger. He's taller than is a nice case study. Is as tall as, is at least as tall as. That's a good one. That's a partial order. So the last thing I wanted to talk to you about is degrees of infinity. And let me stress, this is just for funsies. This is not at all going to be on the exam. But this is just as I think this should be. Okay, so there are some really fun, important sets that set theorists like to talk about. One is n. This is the collection of natural numbers. It starts at 0 and just counts up for all the whole numbers, the non-negative whole numbers. So 0, 1, 2, 3, 4, 5, just keep going. So that's n, the naturals. There are the integers, which are the naturals and all the negative numbers. Which is often with this funny little z. There's q, which is the rational numbers. This is an unfortunate choice of letter now. So this funny q is a rational number, that is any number that can be expressed as the quotient of a fraction. Again, this goes both up and down. And our last one is the reals. And the reals are any number whatsoever. So it doesn't even have to be expressible as a fraction. A nice way to think about it is a value that can be represented as some distance on a number line. So importantly, the reals include the rational numbers, the ones that can be expressed as fractions, and all the irrational numbers. So are people familiar with the irrationals? You probably know one very familiarly. Pi, right? Pi is an irrational number. It's not possible to express it as a fraction properly because it's an infinite number. So, Okay, the reals are big. Again, the naturals, 0, 1, 2, 3, 4. Integers, 0, 1, 2, 3, 4, and same size? How many of them are there? So here's something weird. But one of them is bigger. So here's the weird thing. We can prove that 3 of them are the same size and one of them is bigger. I know that seems fucking weird. This is what I wanted to talk about, right? So N, Z, and Q are the same size. R is bigger. In fact, there's more just in between 1 and 2 on R than there are in N, Z, and Q combined. Let's talk about how we would show this, because this is super cool. First run-up thought. Is the set of even naturals bigger or smaller than the set of naturals? This again. So take 0, 1, 2, 3, 4, going to infinity. Take that collection, that's the naturals. Is the collection of even naturals, that is 0, 2, 4, 6, 8, is that bigger or smaller than my first collection? I mean, intuitively, it feels like it should be smaller, right? There's half as many. What about 1 and 3 and 5? Oh, the odds.
We go on. There's no end. It's the same as
Good.
Space. Space is expanding in such a way that we cannot measure how big it is. That's the whole problem. Although
This one we can measure. Here's the fun thing. We have a yardstick. So here's what we do. The weird thing is these are going to turn out the same. And we can prove them because we can give a perfect mapping between the evens and the naturals. We can show that E fits into N perfectly. In fact, we'll just give it a property. Talk about denumerability. Denumerability is the property where you can be matched up 1-to-1 with the naturals. The size of the naturals is going to be our first infinity. And remember, the naturals are the ones that start 0, 1, 2, 3. All the whole numbers start from 0. Funnily enough, there are an infinite number of infinite sets that are denumerable. That is, we can map up to N. To give you a way to get at it, I'm going to talk to you about a hotel. Let's talk about Hilbert's Hotel. So, Hilbert's Hotel is very big. Hilbert's Hotel, there are a countably infinite number of rooms. That is, the number of rooms is equal to the natural numbers. Right? But the Hilbert Hotel, in this case, is occupied. All the rooms are taken. So let's suppose all the infinite rooms are taken, and then somebody new shows up. We can fit him in. We can fit them in really easily. We accommodate them by telling everybody, move 1 room to your right. That is, if you're in room 1, go to 2. If you're in 2, go to 3. If you're in 3, go to 4. It'll be really annoying, but by God, we can accommodate them. So even if we have the whole room occupied, every position in my infinite chain occupied, I can fit 1 room. And no, it doesn't matter that I pick 1. We can do it with any finite number. Just have everybody move that many spaces over. So cool, we can easily accommodate some finite number. What about an infinite number? So this time, again, our hotel is all booked, everyone's in a room, and all the even naturals show up. Can we fit them in? Yeah. Basically this time, instead of making everybody move one over, we go to whatever number room they're in times 2. And this opens up a new infinite number of rooms. 1 goes to 2, 2 goes to 4, 3 goes to 6. You see how this goes. And now we have all the odd rooms open that can be occupied by our countably infinite new group of people. Again, do we see the trick? It's very cool. So even if we have an infinite number of positions occupied, by manipulating the infinity, we can fit more people in. Yeah. Because there's always more room. Because remember, right? We started at 0, and we have 1, 2, 3, 4, 5, and we just keep counting infinitely. But what we can do is we can manipulate where they are in the chain to put them into new positions in the chain and open up all the places they were. Again, think of it this way. They're all occupying these rooms. If I tell them to go to 2 times whatever their room number was, they're not in these rooms anymore. They're going to be in these rooms. But they're always going to switch to even numbers, right? Because I'm making them move to 2 times whatever their room number was. Again,
It's filled.
it is filled.
Infinite rooms with infinite people in the rooms.
So this is the trick. Again, it's filled. That is, for each room, there's somebody in it. But I can tell them, go to 2, whatever room number you have, go to that number times 2. Everyone's like, fuck, I've got to pack up all my shit and move. So they do. And they move. And as soon as they move, there's a shitload of room. Infinite number of rooms.
We don't understand the cycling, the over hotel, paradox, and YouTube, philosophy.
Again, it's the same thought. We can think about it as again, a mapping. This is the easy way to think about it. It's a mapping. So we're going from, they're all mapped to particular numbers, right? They're all mapped to these numbers. We're now going to map them to these other numbers. And as soon as we do this, our collection here still has 1, 3, 5, 7, but nobody's mapped to them anymore. And with that, I still have space. That's the trick.
How is movement possible?
Again, the movement here is metaphorical, right? It's not literally like people moving. Because otherwise, it'd be a hell of a landmass for the hotel. But again, it's a metaphorical way to get us a grip at this idea of mapping. That's the big trick. Okay. So far, so good. Right? What we've got is this sort of mapping preserves. Here's the last bit. And this is Hilbert Hotel paradox. We can also do it with all of the ones that we can express using fractions. If we express using fractions, we basically write them in a grid like this. We map through our grid, and we can map them 1 to 1 with all the natural numbers too. So we can get all the ones that are expressible by fractions too. But here's the really, really creepy one. There's no way to do this with the reals. So here's why. Here's the really fun one, right? In fact, again, there's more reals in between 0 and 1 than there are naturals. There's more numbers between 0 and 1 on the reals than there are on 0 going as far as you're talking about. As a way to see it, and this is a very fun little argument from Gregor Cantor. Let's suppose we try and do something like the mapping we just did. We'll wrap up real quick. So we write all of them down like this. And note, it doesn't really matter exactly how we're doing the mapping. We try and map them up. And we write it out in this table. Now what we're going to do is we're going to take a diagonal. Let's take the diagonal that starts in our top left and comes down. And we're going to construct a new number. And our new number is going to be whatever numeral you have in each place, add 1. So our new number is going to be 0.2, 4, 6, 8, and we'll have this go to 0, and so on and so on and so on and so on. And the new number we've just constructed cannot be on the line. And it cannot be anywhere in this because no matter where you pick, it will always be one numeral off. Because wherever it intersects, where you thought it was written down, it must be one bigger than the one you've written down. So this is a proof that there's actually going to be at least one size of infinity bigger than what we get with the numbers. We can talk more about this on Friday, because this is super fun. Okay. Cool. So the plan for next week, again, let me stress that the size of infinity stuff is this is fun. This is not, I'm not going to test it. Don't stress, it's fun. We're going to talk more about, we'll do the exam inspection, and we'll talk about sets, and we'll talk about intellectual commitment on Friday. Again, thank you very much for that. Next Tuesday, we're going to talk about possible worlds. The reading is up. There are some questions to do on set theory that's on the Canvas page. We'll talk about all that stuff on Friday. Have a lovely week, and we'll see you all soon.